The sky opens into quiet stars and a darker place where black holes hide. Light cannot get out. That much is clear. So how does gravity still reach us? This question leads from the edge of the event horizon to the core of quantum theory. Entanglement, Bell's theorem, and experiments that confirm spooky action at a distance. Along the way, we face the measurement problem and competing views, many worlds and pilot wave, each asking what we must give up, locality or realism. These threads connect to time, information, quantum gravity, and today's quantum technologies. They reshape how we think about reality, cause and effect, and the limits of knowledge. If this journey resonates, a like and subscribe is appreciated. Let's begin. In 1964, the physicist John Stuart Bell wrote a theorem that changed how we think about reality. He showed that the universe cannot be both local and real in the everyday sense. Local means no influence, jumps across space faster than light. Real means things have definite properties before we look. Bell proved that quantum theory cannot keep both at once. Experiments since then have backed this up many times. The result is plain but hard to accept. Either objects do not have fixed properties until a measurement sets them, or nature allows connections that do not fit our usual idea of cause and effect, tied to light speed. This is not a trick of words. It is a statement about how the world works at the smallest scales we can test. To see why, start with quantum entanglement. When two particles interact and then separate, they can share a joint state. Entanglement means their measured results line up in ways that no ordinary story can explain. If you measure one particle along a chosen direction and get an outcome, the outcome for the other particle is linked to the first when measured the same way, even if the particles are far apart. Local realism would say each particle carried a set of hidden instructions from the start. Bell's theorem shows that no set of such instructions can match the full strength of the observed patterns. The tests use Bell inequalities, which are mathematical limits any local real model must obey. Quantum experiments break those limits. This is not like two gloves in two boxes where finding the left glove tells you the other box has the right. Gloves have their handedness before you open the boxes. Entangled particles do not appear to carry definite properties for all possible measurements ahead of time. The statistics cross the Bell limits, which means the world is not classical under the hood. This raises a sharp worry about faster-than-light influence. It looks as if a measurement here instantly fixes what will be seen there. Yet quantum theory also says you cannot use entanglement to send a message faster than light. The reason is simple, though subtle. The result at each side is random by itself. Only when you later compare the lists from both sides do you see the strong pattern. No one at one lab can choose an outcome to steer the other lab's data. Relativity's speed limit on usable signals stays safe. The link is non-local in the sense of correlations, but it does not carry a controllable cause across space. This balance, non-local correlations, without faster-than-light messaging, is part of what makes the subject feel strange. And yet it is held up in experiment after experiment, with better timing, better isolation, and better closing of loopholes. These facts push us back to the measurement problem, which asks what turns a spread-out quantum state into a single result on a detector. A quantum state, often described by a wave function, gives probabilities for outcomes. It evolves smoothly by the Schrödinger equation until a measurement, and then, in the usual textbook rules, it collapses to one result. But what counts as a measurement? And where is the line between the system and the apparatus? Different interpretations answer in different ways. The many worlds view keeps the smooth evolution, and says all outcomes occur in non-communicating branches. What we call collapse is just our experience inside one branch. Pilot wave theory, also called de Broglie boom, adds hidden positions guided by a wave, keeping realism but giving up locality at a deep level. Other approaches change the math and add rare, real collapses. Some focus on the idea that properties are not absolute, but relational, defined by interactions. None of these pictures has one general agreement because they all fit the same tested equations for lab outcomes. Still, each picture trades something: locality, realism, or the simple textbook rules. Bell's theorem is the sign on the road that says you cannot keep it all. Science often advances by meeting limits like this. We ask clear questions, test them, and keep what nature allows. Quantum theory did not tidy up the old problems of atomic physics. It replaced them with a framework that predicts well while bending intuition. Bell did not end debate. He moved it into sharper form with tools that experiments can probe. Across decades, teams have spaced detectors far apart, changed settings quickly, and used better random choices to remove possible loopholes. The violations remain. The data say the world is not a clockwork made of tiny parts with pre-written values that only wait to be revealed. These results touch old questions about what is out there when no one looks. Some philosophers say the wave function is a real part of the world, like a field, only living in a high-dimensional space. Others say it is a compact way to track our knowledge and expectations. In ancient terms, this sounds a little like asking whether general patterns exist on their own or only in the things we see. Ideas from Buddhist thought, such as dependent arising where things exist through relations and not in isolation, have a family resemblance to the way quantum properties show up in context. The observer effect, which is just the fact that measuring changes what can be known next, invites talk about mind and matter. Most working physicists keep the discussion grounded. The lab facts are clear and the math works. Extra claims about consciousness should be treated with care unless they lead to new tests. Still, it is fair to say, quantum theory has made our picture of reality more relational and less like a set of standalone objects with fixed traits. At the same time, nature has another pillar: general relativity, our theory of gravity. It describes how mass and energy curve space-time and how that curve guides motion, working extremely well for planets, stars, galaxies, and black holes. Quantum theory rules the small. Relativity rules the large. We need one framework that includes both, because black holes and the early universe force the two to meet. This is the search for quantum gravity. One well-known route is string theory. The basic elements are tiny one-dimensional strings whose vibration modes appear as different particles, including a mode that behaves like the graviton. Consistency points to extra spatial dimensions curled up beyond current reach. Notable gains include microstate counts that match black hole area laws in special cases, and a holographic link add SCFT that relates a gravity theory in a space to a quantum field theory on its boundary. These ideas connect fields once thought separate, yet direct string effects likely sit far beyond present energies, and the broad landscape of low-energy worlds makes sharp predictions hard. Other programs seek quantum gravity by different means: discrete spacetime, information-first constructions, while keeping tested parts of quantum theory and relativity. Beyond strings, another line treats spacetime as quantum from the start loop quantum gravity. Loop quantum gravity quantizes geometry itself. Instead of fields living on a perfectly smooth stage, space is built from tiny loops, linked in networks, so area and volume come in discrete steps. At the Planck scale, about 10 to the power of negative 35 meters. In this view, space is grainy, like pixels too small to see. The equations suggest that extreme curvature at a black hole center is replaced by a finite core or a bounce, and early universe models can swap the classical Big Bang for a rebound from prior contraction. Because geometric quantities have discrete spectra, light traveling for billions of years might show minuscule, energy-dependent delays. Teams check photons from gamma-ray bursts, but no repeatable signal has appeared. A central task is to recover ordinary general relativity when distances are large and curvature is gentle, so the discrete picture blends into a smooth one. Another challenge is to include matter fields and the other forces in a unified setting without breaking symmetries that keep the framework consistent. Like string theory's high-energy hurdles, these targets define where evidence could appear and how the theory must meet the world. Other programs approach quantum gravity from different angles. Causal set theory treats space-time as a growing collection of elementary events linked by cause and effect. Geometry then emerges from counting how many events and links lie between 2 points. Asymptotic safety asks whether gravity can be well defined at all energy scales if its effective coupling flows to a fixed point at very high energies. A fixed point would tame infinities without adding new particles. Emergent gravity ideas study whether the geometry we measure is not fundamental at all, but a large-scale average of smaller quantum ingredients, much as temperature and pressure arise from molecules. Information-first approaches try to build space-time from patterns of quantum information, with entanglement stitching regions together and setting distances through network structure. None of these programs is complete. Each offers tools, makes different trade-offs, and points to possible tests. Clues may come from observations that put quantum rules and strong gravity in the same scene. Sharper timing of gravitational waves, traces of very early physics in the cosmic microwave background, and bounds from high-energy collisions or quantum sensors that probe tiny noise and coherence. Fine-tuning questions link quantum theory to the broader problem of why nature's constants sit in life-friendly ranges. The cosmological constant that drives cosmic acceleration is tiny compared with simple estimates of vacuum energy. The fine structure constant that sets the strength of electromagnetism falls in a narrow window that lets stars live long and lets chemistry build complex molecules. Mass ratios among particles shape which nuclei are stable and how stars burn. Small changes can lead to short-lived stars, no heavy elements, or chemistry too weak or too strong for complex structures. The weak anthropic principle points to a selection effect. Observers will only find themselves in regions where conditions allow observers. The strong anthropic principle suggests a deeper reason or purpose behind the match. The many worlds picture of quantum mechanics, paired with eternal inflation or the landscape of possible string theory vacua, provides a setting where physical constants vary across a vast set of regions. So some regions naturally host observers because many possibilities are sampled. Critics argue that selection stories can explain away hard problems rather than solve them, since they are hard to test and can lower the drive to find mechanisms that fix the constants. Supporters reply that if a multiverse follows from otherwise successful models, then using it to explain fine-tuning is a statistical claim, like using planet formation theory to explain why Earth orbits at a life-friendly distance. The dispute turns on what counts as evidence when direct access to other regions is not possible, and on whether indirect signals or internal consistency can play the role that lab tests play elsewhere. Questions about free will meet quantum physics where randomness and cause intersect. Violations of Bell inequalities argue against hidden instructions that fix outcomes for all possible measurements. So the world is not a classical clockwork. Quantum theory, then, assigns probabilities to outcomes that are not determined by prior information. Some see this gap as room for freedom. If not everything is fixed, choice might be real. Others point out that randomness is not agency. If a coin flip decides an action, it does not feel like choice, and replacing the coin with quantum chance does not change that. Compatibilist views hold that freedom lies in actions flowing from reasons and goals in the right way, not in being uncaused. Libertarian views that require indeterminism must show how quantum events in the brain could shape choices without turning decisions into noise. Proposals that tie consciousness to wave function collapse try to bring mind into the physical account by suggesting that experience itself helps select outcomes, but these ideas are speculative and have not produced clear predictions that set them apart from standard quantum theory. Neuroscience can measure many processes in the brain, yet linking those measurements to quantum effects with the needed scale and coherence remains difficult with current tools. Probability in quantum mechanics raises its own puzzles. The Born rule says the chance of an outcome equals the square of the wave function amplitude. It is simple to use and matches experiments, but its status depends on interpretation. In Copenhagen-style views, the rule is taken as a basic postulate that links the math to observed frequencies. In many worlds, all outcomes occur across branches, so a simple branch count would not give the Born weights. To recover them, advocates use arguments from decision theory, symmetry, and self-locating uncertainty to show that a rational agent should weight branches by amplitude squared. Debates focus on whether these arguments assume what they aim to derive. Pilot wave theory adds definite particle positions guided by a wave. The Born rule follows if initial positions match a special equilibrium distribution, while out of equilibrium states could in principle give different statistics, though strong bounds exist. Spontaneous collapse models modify the dynamics by adding rare, real collapses with a small rate that grows with system size, making macroscopic objects behave classically and producing Born frequencies through stochastic jumps. Each route ties probability to a different picture of what is physically real, which is why the same laboratory numbers can carry different conceptual labels. Experiments keep pushing into regimes where classical intuitions fail most clearly. Work with antimatter shows that antiparticles follow the same quantum rules as particles. Interferometers with positrons and antiprotons reveal superposition and, in principle, entanglement, extending tests to mirror matter. Gravity's role is tested with atom interferometry, where ultra-cold atoms take two paths at slightly different heights. Because clocks run at different rates in different gravitational potentials, the two paths accrue different phases, and the interference pattern records proper time, linking quantum phase to general relativity's time dilation. Superpositions of clocks at different heights bring these ideas into a single setup and ask whether time itself can be in quantum superposition when tied to a massive object. Proposals study whether entanglement could stretch across an event horizon, with one partner falling in and the other escaping in radiation, which would clarify how information might be shared or preserved. Hawking radiation is predicted to have a thermal spectrum. The open question is whether subtle correlations in that radiation can encode information about what fell in. Direct tests near real horizons are not yet feasible, so theorists explore analog systems such as sonic black holes in flowing fluids, where similar mathematics applies and where stimulated emission and entanglement can be measured in the laboratory. Quantum field theory in curved space-time provides the main tools for these studies, but full experiments in strong gravity remain rare. Signals from neutron star mergers with extreme densities and magnetic fields open windows where quantum matter and strong curvature both matter. Black hole accretion flows and flares probe plasma under intense gravity, while precise timing of pulsars threads quantum-limited measurements through deep gravitational wells. Cosmology adds another arena. Early universe fluctuations that seeded galaxies came from quantum fields stretched by expansion, leaving patterns in the cosmic microwave background that constrain inflation and any small departures from standard quantum statistics. Small effects tied to Planck scale discreteness, non-locality, or modified dispersion could imprint tiny changes in polarization or phase that careful surveys might detect. Most expected signals are minute and demand careful modeling of astrophysical noise, so existing bounds already rule out simple models that predict large deviations and guide new searches toward narrower targets with better sensitivity and control. To read such faint signals and design unambiguous tests, symmetry links clean mathematics to concrete rules that fix what can and cannot appear in the data. A symmetry is a change that leaves the physics the same, shifting a system in space, rotating it, or sliding it forward in time. Noether's theorem pairs each continuous symmetry with a conservation law, time translation with energy, spatial translation with momentum, rotation with angular momentum. In quantum theory, states live in a Hilbert space, and symmetries act as unitary operations that keep total probability intact. When a symmetry is present, the related operator commutes with the Hamiltonian, so its measured values stay steady. Its eigenvalues label spectral lines and selection rules that tell observers which transitions or polarization patterns are allowed and which are forbidden. These constraints let surveys separate real Planck scale imprints from instrumental artifacts and astrophysical foregrounds, linking fundamental principles to practical analysis. Gauge symmetry extends the idea to local freedom at every point. In quantum electrodynamics, insisting on local phase invariance forces the electromagnetic field to appear, with the photon as its quantum. The electroweak theory uses a larger internal symmetry that ties weak and electromagnetic forces together until it breaks at low energy. Quantum chromodynamics relies on a non-abelian gauge group to describe the strong force that binds quarks. Physicists still debate what gauge symmetry means. One view treats it as a redundancy in our descriptions, where only gauge invariant quantities carry physical content. Another view treats gauge structure as a deep constraint on what laws are even possible. Either way, the demand for local invariance sharply restricts interaction terms and predicts force carriers with specific couplings, which is why gauge symmetry organizes so much of particle physics. Spontaneous symmetry breaking changes the ground without changing the law. The equations can keep a symmetry that the lowest energy state does not share. In a ferromagnet below the Curie point, the material picks a direction, though the laws do not prefer one. In particle physics, the Higgs field has a non-zero value, even in empty space. That vacuum choice breaks electroweak symmetry and gives mass to the W and Z bosons while leaving the photon massless. The mechanism sets a pattern for particle masses and interactions, and predicted a new scalar particle, the Higgs boson, later observed with properties close to the model's expectations. The picture is simple to draw. A symmetric potential with valleys away from the center, a system that settles in one valley, and excitations that reveal mass and coupling once the choice is made. These symmetry links point to a narrow corridor of consistent theories. Requirements like unitarity, causality, and the right notion of locality filter out many possibilities. Inside the allowed set, different symmetry groups, matter contents, and breaking patterns produce different low-energy worlds. Whether symmetry is fundamental in nature or a powerful organizing tool for our models, it disciplines theory space and keeps predictions sharp enough to test. When measurements rule out broad classes of models, those that survive often do so because symmetry forbids dangerous terms that would have spoiled the data. Identity and individuality look different in quantum theory. Identical particles are not tracked by labels. The total state is either symmetric under exchange for bosons or antisymmetric for fermions. This exchange rule is not an add-on. It shapes matter. Bosons can pile into the same state, enabling lasers and Bose-Einstein condensates. Fermions cannot share a single state, which is the Pauli exclusion principle. The reason atoms have layered shells, solids have band structures, and ordinary matter is stable and stiff at everyday densities. The mathematics describes collections rather than name tags. Philosophers note that two quantum particles can share all intrinsic properties and still count as two, which tests the classical principle that indistinguishable things are one and the same. Some argue for a thisness beyond properties. Others say identity is nothing more than the web of qualitative facts. The laboratory facts rely only on exchange symmetry and the statistics it enforces, and those facts control everything from stellar remnants to microelectronics. The same rules drive quantum technologies. A qubit can be in superposition and can be entangled with others, letting certain algorithms cut through problems that swamp classical resources. Fault tolerance is the core challenge. Errors must be detected and corrected before they spread, using quantum error-correcting codes that protect logical information without directly measuring it. If large fault-tolerant machines are built, they could speed up tasks in factoring, optimization, and certain linear algebra problems. Quantum simulation aims straight at many-body physics by mapping hard Hamiltonians to controllable devices. Trapped ions, superconducting circuits, cold atoms in optical lattices, and photonic systems can emulate magnets, exotic phases, and reaction pathways, allowing more predictive design of catalysts, materials, and drugs when classical computation stalls. Quantum communication and cryptography use the fact that measurement disturbs quantum states. Quantum key distribution can establish shared secrets with security grounded in physics, since eavesdropping leaves a trace that parties can detect. Device-independent protocols go further by using Bell inequality violations to certify randomness and entanglement without trusting the internal details of hardware. Quantum networks aim to distribute entanglement across nodes using quantum repeaters, so small processors can cooperate on tasks or share states over long distances. Sensing and metrology push precision toward quantum limits with interference, squeezing, and entanglement. Atom interferometers can measure tiny accelerations and rotations. Quantum magnetometers and gravimeters can probe brain activity, map underground features, and test for slow drifts in fundamental constants. Many of these tools bring benefit without needing universal quantum computers, but they all fight decoherence, the leakage of quantum order into the environment. Social and policy questions Track the technology. If powerful quantum computers appear before post-quantum cryptography is deployed, stored data protected by vulnerable schemes could be read later. That risk motivates a large migration to new standards for banks, hospitals, governments, and infrastructure. Quantum communication can protect high-value links, yet sensing technologies that can see weaker signals through noise may raise privacy concerns if they pierce barriers once thought safe. Engineering focus remains on suppressing noise, designing error-tolerant encodings, and building systems where useful signals can be extracted without washing out the very quantum features that make them powerful. Probability plays a central role in both foundations and applications. The Born rule links the square of wave function amplitudes to observed frequencies. In the Copenhagen family of views, it is a postulate that closes the loop between theory and data. In many worlds, all outcomes occur across branches, so arguments from decision theory, symmetry, and self-location are used to justify amplitude-squared weighting for rational expectations. Critics say these arguments assume what they seek to show. Pilot wave theory keeps definite particle positions guided by a wave and recovers the Born statistics if initial positions follow a special equilibrium distribution, while departures could, in principle, lead to different statistics subject to strong experimental bounds. Spontaneous collapse models add rare, real jumps to the dynamics, giving classical behavior to large systems and fixing outcome frequencies through stochastic processes. The lab numbers match across these pictures, so the choice among them turns on clarity, economy, and the hope for tests that separate them. Symmetry also guides searches beyond the standard model. Demanding larger unified groups can place the strong, weak, and electromagnetic forces inside a single framework at high energy, breaking to the parts we see today. Supersymmetry pairs bosons and fermions and can stabilize mass scales while offering dark matter candidates. Experiments set tight bounds on these ideas, which push breaking scales higher or restrict parameter space. Precision tests hunt for small violations of discrete symmetries, such as charge parity or time reversal. Electric dipole moment searches set strong limits on new phases in interactions. Neutrino experiments test whether lepton number is exactly conserved and whether neutrinos are their own antiparticles, with consequences for why matter dominates over antimatter. Links between entanglement and geometry put symmetry into a broader frame. Holographic duality maps a gravity theory in a higher dimensional space to a quantum field theory on a lower dimensional boundary, translating geometric features into patterns of correlation. Proposals like ER equals EPR suggest that entangled pairs and space-time connections may be two faces of a single structure. Quantum error-correcting codes appear naturally in these dualities, showing how bulk information can be hidden from small boundary regions yet recovered from larger ones. Studying how entanglement spreads, how complexity grows, and how information scrambles in many body systems becomes a way to talk about black hole dynamics and thermalization without invoking a classical picture at small scales. The quantum to classical crossover is treated with decoherence and related ideas. When a system interacts with a large environment, phase information leaks into many degrees of freedom, suppressing interference between macroscopically distinct states. Quantum Darwinism adds that environments make many copies of stable features, so different observers can access the same records without strongly disturbing the system. These mechanisms explain why certain pointer states are robust and why classical facts are shareable. They are dynamical accounts rather than philosophical claims, and they guide design choices, keep coherence where superposition and entanglement are resources, and drive decoherence, where stable readout is needed. Free will debates touch quantum randomness but do not end with it. Bell test violations say outcomes are not fixed by hidden local instructions for all possible measurements. So the world is not a strict clockwork. Indeterminism by itself does not create agency, since random events do not feel like choice. Compatibilist views frame freedom as actions flowing from reasons and values in the right causal pattern, which does not require quantum chance. Libertarian views that rely on indeterminism must show how quantum events in the brain could shape decisions without turning them into noise. Proposals that tie consciousness to collapse remain speculative and have not produced clear, repeatable signatures that separate them from standard theory. Experiments keep testing symmetry and its limits in extreme settings. Atom interferometers place quantum clocks at slightly different heights to track general relativity's time dilation through phase shifts. Antimatter interferometry extends superposition tests to positrons and antiprotons. Astronomers check Lorentz symmetry over long distances and high energies by looking for energy-dependent arrival times or polarization rotation in photons from distant sources. Gravitational wave timing, pulsar clocks, and cosmic microwave background surveys probe small effects that could hint at new symmetry patterns or Planck scale structure. As instruments improve, tighter bounds push aside simple models and shift attention to subtle signatures that cleaner data might reveal. To read those signatures, we also need to understand how real detectors, with noise and dissipation, shape what can be seen. Quantum mechanics and thermodynamics meet where tiny quantum states add up to heat, pressure, and time's one-way flow. The second law says entropy tends to increase. Quantum theory says a closed system evolves reversibly through unitary dynamics that never loses information. The link is coarse graining. A macrostate, set by temperature, pressure, and a few other numbers, covers a vast set of microstates we do not track. As phases and fine correlations spread into many degrees of freedom, the part we measure looks more mixed. The von Neumann entropy of a subsystem rises because information moves into ignored degrees of freedom or the environment. Irreversibility then reflects limited access, typical dynamics from low entropy starts, and continual leakage of phase into surroundings. Quantum information tools make this precise. Mutual information captures shared structure. Relative entropy measures distance from equilibrium. Data processing inequalities formalize that coarse graining cannot create fine detail. In this view, heat and work describe how energy and information split under allowed operations, and the arrow of time follows from preparation, interaction, and forgetting the same ingredients that set real limits for symmetry tests in the lab and in the sky. Measurement is not only readout, it can reshape evolution. The quantum Zeno effect shows that frequent checks of "Are you still in the initial state?" can hold the system in place. Each measurement partly projects the state back. If the checks are rapid compared to the natural transition time, the jump rate drops towards zero. The anti-Zeno effect flips this behavior. With different timing and coupling, repeated probes can speed transitions by opening resonant paths. Which regime appears depends on the spectrum and on the relation between probe interval and the system's characteristic times. Experiments with trapped ions and cold atoms have observed both behaviors by tuning measurement, strength, and cadence. In practice, the Zeno idea stabilizes fragile quantum states, monitor error syndromes, often enough to suppress drift without collapsing the useful superposition. The anti-xenocide informs control. Time your weak probes to steer population into a desired level. Quantum error correction uses gentle, repeated, syndrome measurements that reveal where errors hit without reading the logical bit itself, while pulse sequences and feedback use these measurement-induced effects to guide motion through a complex energy landscape. Contextuality marks a deeper break from classical pictures. The Cochin-Specker theorem proves that one cannot assign pre-existing, measurement-independent values to all quantum observables without running into contradictions, even if you allow non-local hidden variables. In quantum mechanics, the value you obtain can depend on which other compatible observables you measure at the same time the measurement context. This is not the same as uncertainty. It is about logical consistency across sets of observables. Carefully designed tests with spins, photons, and ions violate non-contextuality inequalities, ruling out models that try to attach a fixed answer key to all questions in advance. Contextuality also acts like a resource. Some quantum circuits gain advantage specifically because their statistics cannot be simulated by any non-contextual model. In fault-tolerant schemes, magic states inject the non-Clifford power needed for universality. These states carry contextuality that must be distilled and protected, much like entanglement. Quantum games and protocols turn this into function. By choosing measurement contexts, players achieve correlations no classical strategy can match, and device-independent tasks certify randomness and security using these contextual correlations. Ideas at the gravity frontier tie information to geometry. The ER equals EPR proposal suggests that entanglement and wormhole-like connections, ER bridges, may be two faces of one structure, so patterns of quantum correlation could map to connectedness in spacetime. In the AD, divided by CFT correspondence, a gravity theory in a higher dimensional bulk equals a quantum field theory on a lower dimensional boundary. Bulk geometry translates into correlation functions and entanglement on the boundary. The Ryu-Takayanagi relation sharpens this link. The entanglement entropy of a boundary region equals the area of a minimal surface in the bulk anchored to that region, up to fixed constants. When boundary entanglement changes through dynamics, heating, or coupling, bulk areas shift in step, making geometry a bookkeeping of information. In this view, asking what happens to space and time at the Planck scale may be a category mistake. What is fundamental could be a network of quantum degrees of freedom, whose entanglement and complexity, when coarse-grained, look like distance, curvature, and horizons. Black hole physics puts these ideas under stress. Hawking's calculation gives thermal radiation, which raises the information puzzle. If the spectrum looks thermal, where is the detailed information about what fell in? Black hole complementarity proposes that two observers can have different, self-consistent descriptions that no single observer can test against each other. A freely falling observer crosses the horizon without drama and carries information inward. A distant observer never sees matter past the horizon because near-horizon physics scrambles and re-emits information in the outgoing quanta. Neither view is more real, and no one can combine them operationally. This stance preserves quantum unitarity for outside descriptions and keeps the equivalence principle for infallers. Critics worry about hidden contradictions. Thought experiments imagine decoding detailed information from Hawking radiation and then jumping in to meet supposed copies, challenging no cloning. Firewall arguments claim that if late radiation is highly entangled with early radiation to keep unitarity, it cannot also be entangled with modes just inside the horizon to keep a smooth crossing. Replies point to subtle entanglement patterns, state-dependent interior maps, and quantum error-correcting code structures in holography that encode interior data non-locally, so that no single measurement setup can expose duplication. Thermodynamics returns in this setting in a precise way. Black holes have temperature and entropy. Area behaves like entropy. Surface gravity like temperature. And horizon dynamics resemble standard thermodynamic laws. In holographic models, these become statements about many body systems that heat, scramble, and equilibrate rapidly. Out-of-time order correlators quantify how quickly small perturbations spread, matching expectations for fast scramblers. Entropy growth for accessible subsystems reflects information, leaving simple observables and hiding in complex correlations, while total evolution remains unitary. The same logic that links coarse graining to the second law in ordinary matter carries over. Define the system you can probe, define the environment you cannot, and track which correlations are kept or lost. Quantum thermodynamics studies engines, refrigerators, and batteries at scales where energy exchanges are discrete and coherence matters. Work becomes ordered energy that can be extracted by controlled unitary operations. Heat becomes energy that flows with accompanying entropy. Resource theories formalize constraints, showing which state changes are possible under thermal operations and which require extra resources like coherence or a pure ancilla. Small devices built from superconducting qubits and trapped ions run cycles where performance depends on timing, dephasing, injecting or removing coherence at the right steps, and using feedback to convert information into work in generalized Maxwell-Demon setups. Error correction links directly to thermodynamic cost. Keeping logical qubits clean requires exporting entropy to the environment, which sets heat loads that must be managed in hardware. The Zeno and anti-Zeno effects fit this control picture. Rapid checks or tailored pulses pin a system to protected subspaces, narrowing available transitions and reducing unwanted heating channels, while timed probes boost desired transitions. Dynamical decoupling sequences average away certain couplings, slowing dephasing without heavy measurement overhead. Measurement-based feedback uses partial, weak readouts to nudge evolution with minimal disturbance. These tools are routine in today's labs because they trade small, frequent interventions for large gains in stability. Contextuality has engineering footprints beyond computation. In sensing, choosing measurement contexts lets devices isolate signals that classical noise models would bury, extracting phase and correlation data otherwise hidden. In communication, protocols that certify non-classical behavior with contextuality or Bell-type tests reduce trust assumptions about hardware internals, which is useful when devices come from untrusted vendors. These same ideas support randomness beacons and key generation, whose security rests on observed violations rather than on model details. Transport and chaos in quantum matter close the loop with gravity links. Strongly coupled systems show bounds on diffusion and viscosity that echo gravity bounds near horizons. Holographic duality maps conductivities and diffusion constants to simple geometric quantities at a black hole horizon, giving formulas that laboratory systems can test. Strange metals and ultra-cold atomic gases explore regimes without sharp quasi-particles, where collective behavior and fast scrambling dominate. Measurements of information spread, using echo protocols that access out-of-time order signals, bring what began as a black hole diagnostic into tabletop experiments. Complementarity debates continue as new proposals tie interior reconstruction to outside data through modular flow, and state-dependent dictionaries. Some constructions recover interior operators from the joint system of the remaining black hole, plus its radiation. Others warn that such maps cannot be universal and must depend on the specific microstate. Direct tests at real horizons are out of reach, but analog platforms, optical horizons, flowing fluids, superconducting circuits probe stimulated emission, amplification, and entanglement transport in horizon-like settings, checking the mathematics behind these claims. The common thread is information flow. Which parts become inaccessible under coarse graining? Which correlations set the context for outcomes? How measurements steer evolution? And where entanglement patterns act as scaffolding for geometry. The same lens clarifies quantum measurement in cosmology, where there is no outside lab. If the whole universe is the system, there is no external observer or separate classical apparatus, so the usual Copenhagen split does not apply cleanly. Many worlds keeps unitary evolution with no collapse. Early quantum fluctuations branch into outcomes that later grow into galaxies and voids, raising the question of how ordinary probabilities arise when all outcomes occur. Supporters appeal to decision theory and typicality. Debate remains. The consistent histories approach assigns probabilities to entire cosmic histories when decoherence kills interference between them. Within a decoherence set, standard probability rules hold. Picking the relevant sets can seem ad hoc, and avoiding circularity using probability to justify which probabilities are allowed is difficult. Seen alongside complementarity, both arenas ask the same operational questions. How to define the system? Environment cut without an external observer? How decoherence selects records? And how information theoretic structure anchors predictions when direct experiments are limited. Questions about consciousness and quantum mechanics sit at the edge of science. Brains are warm, wet, and busy. Interactions with the environment cause rapid decoherence, which should crush large-scale quantum coherence long before it could guide thought. Most neuroscientists expect classical descriptions, with neurons firing and networks computing through electrical and chemical signals to explain cognition. A minority view explores whether quantum effects play a role in special parts of cells. One proposal, orchestrated objective reduction, suggests that microtubules in neurons host quantum superpositions that collapse through gravity-linked rules, producing moments of conscious experience. Critics point out that known decoherence rates in such environments are far too fast for stable quantum computation, and that the theory has not delivered distinct, repeatable predictions. Biology does show careful use of quantum effects elsewhere. In photosynthesis, excitations can move through protein networks in ways that look like guided wave-like transport, with coherence surviving long enough to improve efficiency. Some bird species appear to navigate using magnetosensitive chemical reactions where spin states matter, a quantum compass. Lab hints exist for quantum roles in smell. These cases rely on structures that protect coherence at modest scales and short times. They do not show that thought requires quantum mechanics, but they remind us that living systems can exploit physics in clever ways. Symmetry breaking in quantum field theory explains how simple laws yield diverse outcomes. At high energies, the electroweak force is unified. As the universe cools, the Higgs field settles into a non-zero value everywhere. This choice breaks the symmetry and gives mass to the W and Z bosons while leaving the photon massless. The result is a short-range weak force and a long-range electromagnetic force with very different strengths. The Higgs boson discovered in 2012 matches this framework, validating a chain of ideas driven by consistency and symmetry. Early universe phase transitions tied to symmetry breaking could have done more than shape forces. Mechanisms for baryogenesis require departures from thermal equilibrium, CP violation, and reactions that change baryon number. A symmetry-breaking transition can supply the needed conditions. Topological defects such as cosmic strings can form when fields choose different valleys in different regions, leaving lines or walls where choices meet. Such defects could have influenced structure growth if they existed in the right abundance. Some inflation models use symmetry breaking to drive rapid expansion and then end it through a field, rolling into a stable state. These links show how field theory ties particle masses, interaction ranges, and cosmic history into one language. Quantum correlations reach beyond entanglement. Quantum discord measures how much a state's correlations are disturbed by local measurement. States with zero entanglement can still have non-zero discord, which means they carry quantum-only structure that vanishes if you read out part of the system. This broadens the divide between quantum and classical. Some protocols gain benefits using states with discord but no entanglement, achieving speedups in certain model problems or boosting parameter estimation in noisy regimes. The debate over what resource powers quantum advantage, entanglement, discord, coherence, or contextuality depends on the task. For universal fault-tolerant computing, entanglement and non-Clifford resources are essential. For specific sensing and learning tasks in noise, discord-type correlations may capture the useful edge. The practical lesson is to match resource to job and to design hardware and algorithms that protect the relevant type of quantumness rather than chasing a single metric. The interface of quantum mechanics and special relativity lives in quantum field theory. Here, fields fill space, and particles are excitations of those fields. Creation and annihilation operators add and remove quanta. Interactions let excitations scatter and transform. The idea of a particle becomes frame-dependent. An accelerated observer can see a thermal bath, the Unruh effect, while an inertial observer cools the same state vacuum. Particle number is not an absolute property. It depends on the motion of the observer and the slicing of space-time. What remains invariant are the field operators and the correlations they produce. This viewpoint removes confusion about where a particle goes when space-time is curved or when observers accelerate differently. It also explains why event horizons matter. Near a horizon, the split into accessible and inaccessible regions defines which modes count as observable, shaping what different observers call particles. Even the vacuum is lively in field theory. Vacuum fluctuations polarize charges and shift energies. The Casimir effect, an attraction between metal plates, arises because allowed field modes between the plates differ from those outside, changing vacuum energy. Virtual particles in loops alter the strengths of forces as you probe at different energies, a running of couplings that experiments confirm to high precision. The vacuum contributes to particle masses through self-energy corrections and to level shifts, seen in precision spectroscopy. In curved spacetime, vacuum structure produces effects like Hawking radiation at black hole horizons and particle production during cosmic expansion. These are not mere calculational tricks. They leave measurable footprints. Cosmology applies these tools to the early universe. Quantum fluctuations stretched by rapid expansion seed the temperature pattern in the cosmic microwave background and the later web of galaxies. The statistics of those patterns test models of inflation and any departures from simple Gaussian behavior. Quantum fields interacting with the geometry determine how fluctuations grow, which modes freeze, and how reheating fills the universe with particles. Because measurements are limited to one sky and one past light cone, we talk in terms of typicality and variance, not exact repeats. That makes clarity about probability and interpretation more than philosophy. It is needed to connect models to data in a disciplined way. Measurement without an outside observer is modeled using decoherence and coarse-grained histories. As quantum fields interact, phases leak into many inaccessible degrees of freedom, and interference between large-scale alternatives drops. A history where density clumps form here, and one where they form there no longer interfere once long wavelength modes entangle with countless short wavelength modes. Probabilities become stable for those histories, allowing predictions for galaxy clustering and background anisotropies. The method does not require a special collapse event. It relies on dynamics and the practical limits of access. The remaining challenge is to justify the choice of variables and coarse grainings that match what real observers can record without assuming the answer in advance. Speculative bridges keep pushing. If space-time geometry connects to patterns of entanglement, then the early universe's growth of correlations could be read as geometry taking shape. If discord-like correlations survive where entanglement is fragile, they may carry information about processes that standard probes miss. If symmetry breaking set initial conditions for reheating and baryogenesis, its relics might appear as small specific imprints in polarization maps or gravitational wave backgrounds from phase transitions. If particle number is observer-dependent, detector motion in satellite experiments can become part of the design, turning relativistic effects into a tool rather than a nuisance. Across these lines, the same themes repeat in practical terms. Define the system and the environment. Track which correlations survive coarse graining. State clearly which probabilities you mean. And use field theory tools that keep observer-dependent quantities from masquerading as absolute ones. Searching for experimental signs of quantum gravity pushes in two opposite directions. Reach extreme energies near the Planck scale, or build instruments so sensitive that tiny effects add up over long distances and long times. Some ideas look for tiny departures from special relativity at high energy, where photons of different energies might travel at slightly different speeds and arrive from a gamma-ray burst with energy-dependent delays. Others watch for faint quantum jitter in space-time that could leave patterns in gravitational wave signals from black hole or neutron star mergers. Another route tests for small violations of standard quantum rules, such as spontaneous collapse that might be triggered by gravity and would show up when we place larger and larger objects into quantum superposition. Many predictions sit far below what current technology can see, yet space-based detectors for cosmic rays, gamma rays, and gravitational waves keep improving, and laboratory tests push coherence to heavier masses and longer times to close the gap from the other side. Because the Planck energy is about 10 quadrillion times higher than collider energies, direct production of quantum gravity phenomena is out of reach for now. That is why researchers also test the quantum nature of gravity itself. Proposals use delicate interferometers, where tiny test masses become entangled only through their mutual gravitational pull. If gravity can mediate entanglement the way other quantum forces do, that would support a quantum description of the gravitational field. Precision clocks and atom interferometers placed at different heights measure time dilation and phase shifts with quantum accuracy, checking whether gravity treats quantum phases the way general relativity predicts. Cosmology supplies an ancient arena. Traces of quantum gravity could have been written into the cosmic microwave background by processes that ran during inflation, leaving small departures from simple patterns in temperature and polarization maps. Debates about realism and instrumentalism grow sharper around these tests. Scientific realists hold that a theory's success suggests it captures real features of the world, even if parts will later be revised. Instrumentalists treat theories as tools for organizing experience and making predictions without commitment to an observer-independent picture. Quantum mechanics raises the temperature of this dispute. Realists expect an account of what happens during measurement, even if it is unfamiliar. Instrumentalists are satisfied to stop at the rule that links preparation and outcome. Entity realism offers a middle lane. We should believe in electrons, photons, and qubits because we manipulate them to build devices and probe other systems, even if we remain cautious about stories that go beyond what experiments require. Structural realism focuses on the mathematics that survives theory-change relations, symmetries, conservation laws, arguing that this shared structure is what our best theories reveal. The measurement problem sits at the center of these positions. If unitary evolution never breaks, where do definite outcomes come from? And why do we see single results rather than superposed records? Collapse models add a small, state-dependent randomness to the dynamics, aiming to deliver outcomes and explain classical behavior for large systems. Many worlds keeps unitarity for all systems and locates definiteness inside branches selected by decoherence. Pilot wave theory keeps definite particle positions guided by a wave, trading locality to keep realism. Each route matches lab statistics, so the dispute turns on clarity, economy, and whether any option will make a new, testable prediction at accessible scales. Future experiments could change the terrain. Quantum computers with millions of fault-tolerant qubits would run long quantum processes that test interference and error correction principles far beyond today's regimes. Any small deviation from standard rules might accumulate and become visible as a pattern of faults or as limits on circuit depth. Space missions could test entanglement across planetary distances and probe how gravity acts on quantum links between satellites and ground stations. Laboratory work aims to place nanoparticles, tiny membranes, or superconducting circuits into spatial superpositions and monitor them for collapse-like behavior as mass grows. If the collapse rate increases with size, measurements could map that growth and separate gravity-linked models from environment-induced noise. Quantum biology may add surprises. Photosynthesis and bird magnetoreception already show that life can protect coherence for function at modest scales and warm temperatures. Careful tests will check whether similar tricks appear elsewhere. While most researchers still expect classical models to explain higher-level brain function, philosophical views adapt as data arrive. If future observations find clean energy-dependent photon delays that match discrete space-time predictions, realists would treat the delay law as a window into microstructure, while instrumentalists would treat it as a rule for timing corrections. If gravity-mediated entanglement is observed between tiny masses, that would push against models where gravity is strictly classical. If massive object superpositions remain stable up to new scales with no sign of extra noise, collapse models would face tight bounds. Each outcome narrows possible stories about what reality is like beneath the equations and whether measurement needs new physics or only better bookkeeping of system, apparatus, and environment. The historical path to today's questions began with tension between quantum predictions and classical intuition. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen argued that the quantum description of two separated particles leads to a paradox. If two particles interact and then fly apart, measurements on one can be used to predict, with certainty, results on the other for a matching property. If no influence can travel faster than light, then the distant particle must already carry the value that the measurement will reveal. Otherwise, the local measurement would have to reach across space instantly, which clashed with Einstein's sense of locality. EPR concluded that quantum mechanics must be incomplete and that a deeper theory with hidden variables should restore local realism. Definite properties independent of observation plus no faster than light influence. Thought experiments turn this idea into the familiar Alice and Bob setup. Alice measures one property of her particle, Bob measures the matching property of his, and the outcomes line up more tightly than any simple classical picture would allow. The quantum state predicts perfect correlations for certain settings, even though no signal is exchanged at measurement time. If you imagine that each particle carries a list of answers written at the time of separation, the list must work for all measurement choices Alice and Bob might make later. For many years, this remained a philosophical argument because no one knew how to check whether such pre-written lists could reproduce all the quantum statistics. John Bell's work changed the situation by translating the debate into inequalities that any local hidden variable model must satisfy. Experiments could then compare quantum predictions, hidden variable limits, and actual data. As techniques improved, tests with photons, ions, and electrons closed loopholes, one by separating detectors far apart, choosing settings at the last moment, and increasing efficiency. The observed correlations broke Bell's limits, which rules out the entire class of models that combine locality with pre-assigned outcomes for all possible measurements. That result does not tell us which interpretation of quantum mechanics is right, but it sets a boundary that any deeper theory must respect. It also defines the kind of non-local correlation that devices can harness without enabling faster-than-light communication, shaping today's work in quantum networks, cryptography, and randomness certification. In 1964, John Stuart Bell turned the EPR debate into testable physics. Working at CERN, he proved that any model that keeps both locality and hidden variables must obey strict statistical limits on correlations between distant measurements. These limits Bell inequalities draw a hard boundary. If each particle carries pre-written answers and no influence travels faster than light, then certain combinations of measured correlations cannot exceed a fixed value. Quantum mechanics predicts stronger correlations that cross the boundary. The prediction invites an experiment. Prepare entangled pairs. Let two observers choose measurement settings independently and far apart, and compare results over many trials to see which side of the boundary nature chooses. A simple way to picture this uses spins or photon polarizations measured at different angles. In a local hidden variable model, the outcomes are set in advance for every possible angle, and the observed correlation is just an average over those pre-written lists. Bell showed that the mathematics of such lists limits how strong the correlations can be across all angle choices. Quantum theory, by contrast, assigns joint amplitudes to the pair and turns angle choices into interference patterns within those amplitudes, producing correlations that exceed the local hidden bound. The point is not that quantum mechanics lets signals jump across space. It is that the statistics of joint outcomes do not fit any picture where distant results are fixed in advance without non-local structure in the underlying description. The most common test uses the CHSH inequality, named for Clauser, Horn, Shimony, and Holt. Two observers, often called Alice and Bob, each choose between two settings. From the data, they compute a number S that combines 4 correlation coefficients. Any local hidden variable theory obeys S is less than or equal to 2. Quantum mechanics predicts values up to 2. Square root 2 is approximately equal to 2.828 for well-chosen settings and ideal states. This gap is large enough that real experiments with noise can still show a violation if they keep losses and errors low. It is a clean target. Prepare entanglement, randomize settings, collect counts, compute S. Experiments began in the 1,970 seconds. John Clauser and collaborators used atomic cascades to create entangled photons and measured polarization at separated stations. In the early 1,980 seconds, Alain Aspect's team improved the setup with fast, random switching of analyzer orientations while photons were in flight. This change attacked a key worry that hidden communication between stations might coordinate outcomes. The data violated the CHSH bound and matched quantum predictions, with S values near 2.7 under good conditions. These early runs had limitations, losses in detectors, limited separation, and timing windows that left room for loopholes, but they established that the quantum side of the boundary was reachable in practice. 2 main loopholes became the focus. The detection loophole arises when many pairs are created, but only a small fraction are detected. If hidden variables could decide which pairs get recorded, they might fake a quantum-like violation in the detected subset. The locality loophole appears if settings are not chosen and implemented fast enough, or if the stations are too close, leaving time for a light-speed signal to pass between them after the settings are chosen. Over the next decades, experiments improved detectors, increased distances, and tightened timing, closing these loopholes one at a time in different platforms: photons with better photodiodes, ions with higher detection efficiency, and larger separations with faster electronics. In 2015, several teams closed both loopholes at once. At Delft, the Hansen group entangled electron spins in nitrogen vacancy centers in 2 diamonds, separated by more than a kilometer. They heralded successful entanglement events and used high-efficiency spin readout, addressing detection while choosing settings rapidly and independently to enforce locality. Groups in Vienna and Boulder used entangled photons with highly efficient superconducting detectors and careful space-time layouts so that each station's choice and measurement were space-like separated from the others. All reported statistically strong violations, many standard deviations beyond the local bound, leaving no room for local hidden variable explanations. These achievements, building on decades of work, set the stage for the 2022 Nobel Prize in Physics, awarded to John Clauser, Alain Aspect, and Anton Zeilinger. Bell violations force a choice. You cannot keep both locality, in the strict EPR sense, and realism, defined as pre-existing values for all potential measurements. Different interpretations give up different pieces. Pilot wave theory keeps definite positions, but accepts non-local guidance. Many worlds keeps locality of the underlying Schrödinger evolution, but discards single outcome realism at the global level. Collapse models modify dynamics to produce outcomes, but then must manage how collapses respect relativistic structure. The data do not pick a winner, They draw the boundary that all contenders must respect. A separate question asks why such non-local looking correlations cannot be used to send messages faster than light. The no signaling theorem answers it. For each side alone, the outcomes look random. Only after Alice and Bob compare their lists do the patterns emerge. Nothing Alice chooses can change the statistics Bob sees locally. The joint distribution violates local realism, but the marginal distribution at each site stays unaffected by the other's setting. This preserves the operational content of relativity, while allowing non-local correlations in the global description. Experiments make no signaling checks part of their analysis. They look for any dependence of one side's outcome distribution on the other side's setting and bound it tightly. Modern runs also randomize settings using high-speed physical randomness and sometimes cosmic photons to avoid hidden biases. Space-time diagrams confirm that setting choices and detections are arranged so that no subluminal influence can coordinate them. The pattern remains. S exceeds 2 inches, line with quantum theory, while local statistics stay insensitive to the distant knob, in line with relativity. The size of observed violations matches the quantum maximum once losses and imperfections are accounted for. Typical high-quality photonic tests report S around 2.7 to 2.8 when detection and visibility are high. Solid-state and atom-ion platforms often trade some visibility for other advantages, such as better detection or longer separations, yet still clear the bound by many standard deviations. Each platform brings different systematics, background counts, alignment, drift, memory effects, and each run includes detailed checks that they cannot conspire to fake a violation. Bell tests now support practical tasks. Device-independent quantum key distribution uses a violation to certify the presence of entanglement and genuine randomness, even when the internal workings of devices are untrusted. Randomness expansion protocols turn a small seed of randomness into a longer certified string by observing a sustained Bell violation. These tasks rely on exactly the features that make Bell tests powerful: the ability to infer non-classical correlations from statistics alone, plus the no signaling condition that binds what adversaries can do without being detected. The distinction between different notions of locality helps align Bell results with relativity, parameter independence, the idea that one side's setting does not change, the other side's marginal distribution remains intact. Outcome independence, the idea that one side's outcome is independent of the other's outcome, given the settings fails in quantum theory. Bell's theorem rules out models that keep both when paired with realism. Relativity demands the former for causal structure. Quantum non-locality shows the latter cannot hold in any model that keeps pre-assigned outcomes. The two frameworks meet operationally. No superluminal signals, yet non-local correlations in joint statistics. Modern variations continue to probe foundations. Some runs enforce independence of settings by sampling cosmic light as a randomizer, pushing any hypothetical coordination back billions of years. Others explore multipartite inequalities, high-dimensional entanglement, or long-distance links over fiber and satellite to test stability outside the lab. Parallel work studies Leggett type and local-friendly models that try to relax different assumptions. Results place strong bounds on such alternatives. The landscape that remains must accept that quantum predictions for correlations are not a residue of ignorance about local properties, but reflect structure that resists any classical decomposition. The EPR story that began with a worry about spooky action now defines practical benchmarks. Prepare clean entanglement. Choose settings far and fast. Collect enough data. Test for no signaling. And compute S. If the bound is broken, local hidden variables are out. If, on top of that, randomness and security claims are tied to the size of the violation, the same experiment becomes a tool. The boundary Bell drew continues to organize both our conceptual maps and our engineering checklists. According to the Copenhagen view shaped by Niels Bohr and Werner Heisenberg, a quantum system is described by a wave function that can place the system in a superposition several possible states at once. The Schrödinger equation gives a smooth, deterministic evolution for that wave function when no measurement is happening. A measurement, by contrast, produces one definite result. The usual story says the wave function collapses to the state, matching that result. The trouble is that the theory does not specify what counts as a measurement, who or what triggers collapse, or where the line sits between quantum behavior and classical readout. The equations offer two rules that do not look like the same kind of process: continuous evolution and sudden collapse. That mismatch is the measurement problem in plain form. Many competing ideas try to remove the mismatch without breaking the math that matches experiments. One direction treats collapse as an illusion and keeps only unitary evolution. Another direction keeps a single world with definite properties at all times by adding extra variables that the standard formalism does not track. A third direction changes the dynamics slightly so that collapse becomes a genuine physical process. A fourth direction treats quantum states as personal assignments of belief rather than as features of the world. Each route preserves the successful predictions while shifting what we say the theory is about. The many worlds interpretation, proposed by Hugh Everett, keeps unitary evolution at all times and never adds a collapse postulate. When a detector becomes entangled with a system, the joint wave function spreads into branches that record different outcomes. Each branch contains a version of the apparatus, the observer, and the environment that agree on one result. No special split is added on top of the Schrödinger equation. Branching is just widespread entanglement that prevents different records from interfering. In this view, measurement is not a special act. It is an ordinary interaction that correlates systems. The price is high if you think the word real should apply to only one outcome. Supporters answer that the price is fair because nothing extra is added to the mathematics, and because decoherence explains why branches stop affecting one another. A persistent issue is probability. If all outcomes occur, why should an agent weight them by the Born rule, amplitude squared? Arguments based on decision theory, symmetry, and self-location try to show that a rational agent inside the theory must use Born weights. Critics reply that these arguments smuggle in what they aim to prove. Pilot wave theory, also called de Broglie-Bohm, moves in a different way. It adds definite particle positions guided by a wave that obeys the Schrödinger equation. The guidance law is non-local. The velocity of one particle can depend on the positions of others through the common wave. Outcomes are determined by initial positions together with the guiding wave, so randomness reflects our ignorance of those positions. This keeps realism particles always have locations and explains sharp results without collapse. It also accepts non-local influence at a fundamental level, which sits awkwardly with special relativity unless one adds extra structure to define a preferred slicing of time. Extending the model to full quantum field theory with particle creation and annihilation is technically demanding, though versions exist for certain cases. Admirers value the clear ontology, Detractors see unnecessary machinery compared to the compact standard rules. Spontaneous collapse models change the dynamics instead of the ontology. The GRW model, Ghirardi-Rimini-Weber, postulates rare, random, localization events for each particle, with a tiny rate per particle, but an amplified effect for large systems containing many particles. Microscopic systems then evolve almost always by the Schrödinger equation and can show long-lived superpositions. Macroscopic objects suffer frequent effective collapses because the probabilities add up across many constituents, so they appear in definite positions. Collapse becomes a physical process, not a rule about knowledge. The models introduce new parameters, collapse rate and localization width, that must be chosen to fit observations, and in many versions, they imply a small energy increase over time. Experiments push on these parameters by creating larger and larger matter wave superpositions and by searching for excess heating or noise. No deviation has been confirmed so far, which sets bounds and shapes future designs. Copenhagen-style views survive by treating the wave function as a tool for predicting outcomes rather than as a direct picture of the world. Collapse is a rule for updating that tool when new data arrive. Decoherence explains why certain results become stable records once a system interacts with many environmental degrees of freedom, because phase information leaks into the environment and interference between macroscopically distinct records dies away. What Copenhagen does not supply is a single, detailed account that covers system, apparatus, and observer, all within one quantum model without switching rules. Advocates argue that demanding such a global account may be asking for the wrong kind of story, since physics is about links between preparations and outcomes. Critics want a clean line between unitary motion and outcome selection stated inside the theory. Cubism, quantum Bayesianism, leans into the predictive tool view and makes it explicit. A quantum state is an agent's personal assignment of probabilities for future experiences. The Born rule is a normative rule telling the agent how to keep assignments consistent across possible experiments. A measurement outcome is an experience for that agent. Collapse is simply updating beliefs after learning the outcome. Different agents can assign different states if they have different information, and there is no contradiction. This dissolves the measurement problem because there is no objective state that needs to collapse. The cost is heavy if one expects physics to describe an observer-independent reality. Cubists answer that what physics gives are stable rules for expectations, and that insisting on a global, agent-free state goes beyond what experiments can ever decide. Differences among the interpretations show up in how they treat non-locality. Many worlds keeps local equations, but denies a single outcome realism at the global level. Pilot Wave keeps realism and single outcomes, but builds in non-local guidance. Collapse models keep single outcomes and try to keep locality approximately, yet must specify how collapses fit into relativistic spacetime. Copenhagen and Cubism avoid taking a stand on underlying mechanisms and focus on the operational content. No faster-than-light signals, correct probabilities, stable records. Bell tests tell us what any deeper account must include. You cannot keep both locality and pre-existing values for all possible measurements. No signaling tells us what must be preserved. Local outcome statistics may not depend on faraway setting choices. Any story that claims to be a completion has to fit inside those boundaries. Decoherence and environment-induced superselection explain why some variables look classical. Pointer states, those that dump the least information into the environment tend to survive. That is why position-like variables for macroscopic bodies stabilize, while delicate phase relations vanish quickly. Decoherence does not produce a unique outcome by itself. It explains why interference between different macroscopic outcomes is unobservable in practice. Many worlds reads this as branch isolation. Pilot wave reads it as the wave guiding definite positions into classical-looking patterns. Collapse models add genuine jumps that finish the job. Cubism reads it as the point where the agent updates because a record has formed. Tests continue to probe the edges where the stories might diverge. Interference with ever larger masses and longer times looks for collapse-like noise. Experiments try to witness gravity-mediating entanglement between tiny masses, which would support quantumness of the gravitational field rather than a classical background. Device-independent protocols use Bell violations to certify randomness and security, leaning on the same features that make non-locality a boundary condition for theories. Precision control of small quantum systems checks whether Born rule frequencies hold across deep circuit depths and complex error-corrected evolutions. So far, standard quantum mechanics passes these checks. Bounds push alternative parameters into tighter corners. Simple language helps keep the landscape clear. The measurement problem is the tension between smooth evolution and sharp outcomes. Many worlds removes collapse and spreads outcomes across branches. Pilot wave adds particle positions and non-local guidance to keep single outcomes. Collapse models tweak dynamics to produce real collapses with tiny side effects. Copenhagen treats collapse as a rule of thumb for predictions. Cubism treats it as belief updating by an agent. All match current experiments. They differ in what they ask us to regard as real, what they are willing to give up, and what they predict could break first if new phenomena appear. Links to relativity and information run through each view. Any acceptable account must respect no signaling, even while accommodating Bell-type non-local correlations. Any acceptable account must explain why classical records are robust and why interference is hard to see beyond small systems. Any acceptable account must tell us how probabilities enter a world described by amplitudes. Work on decoherence, quantum Darwinism, and error correction continues to supply the technical pieces that any interpretation must use, whatever story it tells about reality under the hood. The idea that consciousness causes collapse traces back to early attempts to place a clear cut in the measurement chain. John von Neumann showed that, in principle, you can treat the measuring device and even the observer's body as quantum systems that become entangled with the particle being measured. If everything is quantum, the chain continues with no natural stopping point. He argued that the sequence must end somewhere, and some readers took the final cut to be in the observer's mind. Eugene Wigner sharpened the issue with his friend's scenario. A friend inside a sealed lab measures a quantum system and writes down a result. From outside, Wigner can treat the whole lab, friend, device, and notebook as a single quantum state that evolves without collapse. Inside the lab, the friend experiences one definite outcome. The two descriptions seem to conflict. Wigner suggested that consciousness might select one outcome, forcing the collapse that the equations do not provide by themselves. Modern versions stack multiple friends and multiple outside observers. They show that different observers can assign different quantum states to the same physical situation and, under certain assumptions, can be led towards statements that cannot all be true at once. These constructions do not prove that minds collapse wave functions, but they do press on the idea that all observers must agree on a single set of facts. Most physicists doubt that consciousness is the missing physical ingredient. The main worry is that such proposals move the problem rather than solve it and invite vague, untestable claims about minds. Decoherence theory offers a concrete, dynamical account of why measurements appear to have outcomes without appealing to subjective experience. Real systems are never perfectly isolated. Photons, air molecules, lattice vibrations, and thermal radiation all interact with the system and carry away phase information. The system becomes entangled with a vast environment, and interference between macroscopically distinct states becomes unobservable in practice. The combined system plus environment remains in a pure superposition, but any small part we examine looks mixed. For macroscopic objects at room temperature, the timescale for this loss of observable coherence can be tiny, down to femtoseconds for position-like states, so we do not see chairs in two places at once. Decoherence also explains why certain variables behave classically first. Position tends to decohere much faster than delicate phase relations or certain internal degrees of freedom, picking a pointer basis that matches stable records on detectors and in memory. The approach accounts for why detectors end up with robust readings and why multiple observers can agree on those readings after the fact. It does not, by itself, select a single result from the still present superposition of possibilities. That final step depends on which larger picture you adopt. Many Worlds says no extra step is needed because each branch contains its own record. Pilotwave assigns definite particle positions at all times, so the record is just where the particles went. Spontaneous collapse models add rare physical jumps that remove superpositions for big systems. Copenhagen-type views treat collapse as an update rule tied to the way experiments are described. Cubism treats it as belief updating by an agent. Decoherence is the common engine that makes records stable in all these stories. Experiments push these ideas by building larger, cleaner superpositions, and by monitoring how fast coherence is lost under controlled conditions. Matter wave interferometers have handled molecules with hundreds of atoms, showing clear interference fringes when the environment is quiet enough. There is a steady drive to extend this to nanoparticles and micromechanical membranes, cool them close to their ground states, and place their centers of mass into spatial superpositions. If any collapse-like noise grows with mass or size, these platforms can expose it by deviating from standard interference patterns or by showing unexplained heating. Parallel work uses levitated particles in ultra-high vacuum and cryogenic shields to reduce ordinary noise and isolate any new effect that might be linked to gravity or other beyond quantum mechanisms. Quantum computers make superposition and entanglement into working tools. A qubit is a two-level system that can hold a superposition of 0 and 1. Many qubits can be entangled so that their joint state carries patterns no collection of independent bits can match. Google's 2019 demonstration used a 53-qubit device to sample from a distribution that is hard to reproduce on classical machines. The practical value of that specific task is modest, but it showed that controlled quantum evolution can be deep enough to produce outputs beyond straightforward classical simulation. Since then, groups at IBM, IonQ, and others have expanded qubit counts, coherence times, and gate fidelities while moving toward error correction. The main obstacle is decoherence and noise, which corrupts states and gates on microsecond to millisecond timescales in many platforms. Quantum error-correcting codes spread logical information across many physical qubits so that local errors can be detected and repaired without learning the logical state. Threshold theorems say that if error rates are pushed below certain values, arbitrarily long computations are possible in principle. In practice, one stable logical qubit can require hundreds to thousands of physical qubits, depending on hardware and target error rates. So scaling is a central engineering challenge. Quantum communication uses the same rules to protect information. Quantum key distribution protocols such as BB84 encode bits in the polarization of single photons. Any eavesdropper who measures those photons in transit will disturb them in a detectable way, because unknown quantum states cannot be copied. Field tests have linked cities over fiber and, with China's Messias satellite, demonstrated key exchange over more than 1,000 kilometers between ground stations. Similar efforts in Europe and the United States aim to build regional and intercontinental quantum links and to integrate quantum repeaters that can extend range by storing and purifying entanglement. Quantum teleportation, which uses pre-shared entanglement plus classical communication to reconstruct a quantum state at a distance, is a core primitive for such networks. It does not send anything faster than light, yet it allows fragile states to be transferred without crossing noisy channels directly. Tests of quantum mechanics in extreme regimes provide additional leverage. Tabletop experiments cool mechanical resonators to near their ground states and monitor them at levels where one quantum of vibration matters. Atom interferometers place atoms in superpositions that traverse paths separated by macroscopic distances and recombine with phase control tied to gravity and rotation, letting researchers check how quantum phases accumulate in different gravitational potentials. Precision experiments with superconducting circuits probe entanglement and interference across long gate sequences to see whether any small rule change piles up into a measurable drift from the Born rule. At larger scales, gravitational wave observatories are reaching quantum limits on displacement sensing and use squeezed light to push past shot noise, making these instruments both users and testers of quantum principles. Proposals to read quantum fingerprints in astrophysical signals exist, though most predicted effects are far smaller than current sensitivity. Consciousness-based collapse remains a minority view in this landscape. Its main claim that a conscious observation is special has not yet produced a mechanism that fits into the broader structure of physics, or a clear experimental signature that sets it apart from decoherence plus standard dynamics. Modern Wigner-Friend-type thought experiments do show that different observers can hold different state assignments, and that combining those assignments can lead to conflict if one assumes a single, global set of facts that every observer must share. Possible responses include accepting observer-relative facts, restricting which inferences are allowed across nested observers, or adopting interpretations where no single collapse event has to be shared across all descriptions. In each case, decoherence still does the heavy lifting that turns delicate quantum phases into stable classical records in the settings where real measurements occur. Practical work continues to map where quantum behavior fades into classical appearance and why. Engineers reduce unwanted couplings with better materials, shielding, and pulse sequences. They also use measurement and feedback to stabilize states that would otherwise decay. Physicists quantify how quickly environments record information about certain variables and how that recording makes those variables the ones that appear classical. Computer scientists design error-correcting codes and fault-tolerant protocols that treat noise as a predictable resource to be countered. Communication scientists build channels whose security follows from the same no cloning and no signaling features that Bell tests highlight. Biophysicists look for controlled quantum effects in warm, wet settings and test whether coherence can be maintained long enough to be useful. Across these efforts, the same pieces recur: superposition, entanglement, decoherence, and careful bookkeeping of what is measured, what is ignored, and how information flows between a system and its surroundings. Quantum mechanics treats time differently from space. In standard quantum theory, time is an external parameter that we plug into the Schrödinger equation to see how a state changes. Space, by contrast, has operators for position and momentum with uncertainty relations. There is no comparable time operator with a universal uncertainty rule. This split collides with general relativity, where space and time form a single geometry that bends and evolves. The mismatch raises basic questions: whether a measurement is instantaneous, whether a collapse, in interpretations that use it, would take time, and how to talk about clocks that are themselves quantum. In quantum gravity, the issue sharpens. If geometry becomes quantum, there should be no outside time to lean on. Canonical approaches lead to the Wheeler-DeWitt equation, a constraint on the wave function of the universe that has no time variable at all. Dynamics must be encoded in relations among variables, not in evolution with respect to a background clock. One proposal by Page and Wouters replaces external time with internal correlations. Split a closed system into a clock and the rest. If the joint state has the right entanglement, conditioning on the clock's reading makes the rest appear to evolve. Time is then an emergent label extracted from correlations. Laboratory tests with entangled photons and trapped ions have mimicked parts of this idea, showing that conditional states can reproduce the look of evolution. Relativity adds its own twist. Clocks at different heights in a gravitational field run at different rates. With quantum clocks, you can put a single clock into a superposition of heights and ask how its tick rate behaves. Interferometry experiments with atoms and ions support the view that phase, the quantum proxy for timekeeping, accumulates in line with gravitational time dilation. This brings two pillars together: quantum phase evolution and relativistic redshift agree within the limits measured so far. Black holes create a different tension. Hawking's calculation showed that black holes radiate thermally and can evaporate. If the radiation is exactly thermal, it carries no information about the details of what fell in. A pure quantum state falling into a black hole would then evolve into a mixed thermal state of final radiation, violating unitarity. The information paradox is the conflict between Hawking's thermal spectrum and quantum mechanics' demand for information-preserving evolution. The paradox becomes sharp because the radiation far away seems independent of what formed the whole, while the interior holds the data behind an event horizon. Several ideas try to align the pieces. Black hole complementarity says two descriptions can both be valid, but for different observers. A distant observer sees information stored and scrambled near a stretched horizon and later encoded in the radiation. An infalling observer experiences nothing special at the horizon of a large black hole and carries information inward. No one observer can test both stories, so no contradiction appears operationally. The holographic principle provides a broader frame. The amount of information inside a region scales with its boundary area, not its volume. AD-CFT makes holography concrete by equating gravity in a bulk spacetime with a quantum field theory on its boundary. In that duality, black hole evaporation is unitary because the boundary theory is unitary. Information that looks lost in the bulk is encoded non-locally on the boundary. The firewall argument tests how far these claims can go. If late Hawking radiation is maximally entangled with early radiation to preserve unitarity, it cannot also be fully entangled with interior modes in the way required for a smooth horizon. The monogamy of entanglement blocks both at once. One response links outgoing pairs to interior geometry via ER equals EPR, suggesting that entanglement and wormhole connections are two descriptions of the same structure. Another points to quantum error correction in holography. Bulk operators, including interior ones, can be reconstructed from different boundary regions with redundancy that protects information from local erasures. Recent island calculations reproduce the expected page curve, the rise and later fall of radiation entropy, by adding certain interior regions to what counts as the radiation's entanglement wedge, hinting that the bookkeeping of quantum information can repair the apparent loss. Quantum mechanics also shapes the larger structures we see. Inflation theory says the very early universe expanded exponentially for a brief period. Quantum fluctuations in fields were stretched to astronomical sizes, freezing in as classical density variations once their wavelengths exceeded the horizon. These variations later grew under gravity into galaxies and clusters. Measurements of the cosmic microwave background map the tiny temperature differences left by these fluctuations. Their statistics nearly scale invariant, nearly Gaussian, with a specific acoustic pattern match the predictions of quantum fields stretched by inflation. The pattern ties small-scale quantum uncertainty to large-scale structure. The measurement problem reappears in this setting. If early perturbations began as quantum superpositions, why do we see a single pattern of density today? Decoherence supplies an answer consistent with several interpretations. As modes interact with many other degrees of freedom, other fields, gravitational perturbations, and the environment they effectively create, phases between different large-scale configurations are spread and lost to local observers. Each coarse-grained history becomes dynamically independent. Many worlds reads this as branching into distinct, classical-looking universes. Collapse models claim that a small, dynamical noise picked one pattern. Copenhagen-type views say the question is ill-posed without an explicit measuring setup, but agree that predictions for observed correlations are those of decohered histories. Decoherence itself does not choose a unique outcome. It makes interference between macroscopic alternatives irrelevant for predictions tied to local records. Quantum cosmology tries to write a single wave function for geometry and matter. The Wheeler-DeWitt equation encodes constraints that any allowed state must satisfy. Interpreting it needs a clock variable and a notion of probability. The Hartle-Hawking no-boundary proposal defines the universe's initial state by a path integral over smooth, compact geometries without an initial boundary. In semi-classical approximations, this can yield a state that favors inflationary expansion and smooth large-scale structure. Other approaches explore different boundary conditions or histories, such as tunneling proposals. Penrose's conformal cyclic cosmology sketches a sequence of aeons in which the far future of one, stretched and smoothed, maps to the Big Bang of the next through a conformal rescaling, with possible signals preserved in long wavelength patterns. These ideas remain speculative, but keep the focus on how quantum rules, boundary choices, and geometry cooperate to set initial conditions. Time's arrow fits into this picture through low entropy beginnings and typical dynamics. If the early universe began in a special, low entropy state, then ordinary interactions move most accessible subsystems toward higher entropy as correlations spread. In a quantum account, the von Neumann entropy of small parts tends to rise as they entangle with the rest. Coarse graining turns hard to access phases into missing information that we track as thermodynamic entropy. Gravity adds structure because low gravitational entropy means a smooth mass distribution, while clumping increases entropy by opening many more microstates. The growth of structure, the formation of stars and black holes, and the thermal histories of matter and radiation can all be read through that lens. Experiments and observations that touch these themes keep expanding their reach. Quantum clocks compare tick rates over centimeters of height with enough precision to see gravitational redshift. Atom interferometers test phase accumulation in superposed paths at different potentials. Observations of the microwave background's polarization search for traces of primordial gravitational waves that would point to specific inflation models. Gravitational wave detectors measure signals from merging black holes and neutron stars with quantum-limited readout, and future observatories aim to read finer features that could reveal how horizons and strong fields handle quantum noise. Tabletop tests continue to combine low temperature, high vacuum, and careful isolation to watch large objects for deviations from standard quantum behavior that could hint at new ingredients. Across these lines, tools from quantum information theory connect to geometry and dynamics. Entanglement, entropy, diagnoses which parts of a system share information and which parts act as effective environments. Relative entropy and recoverability bounds constrain how much data can be reconstructed from fragments, feeding into holographic error correction pictures. Complexity measures track how hard it is to reach a state from a simple reference and may map to bulk geometric features in dual descriptions. These links give operational meaning to statements about emergent time and space by tying them to quantities we can calculate and, in some cases, measure. The open questions are framed in practical terms. How to define time without an external clock inside a fully quantum closed system. How to preserve unitarity in black hole evaporation while keeping local experiences smooth for infalling observers. How to extract initial condition rules from quantum cosmology that match sky maps. How to read entanglement patterns as geometry in general settings beyond special dualities. How to design experiments that put quantum clocks, superpositions of mass, or long baseline entanglement into regimes where tiny effects can be resolved. The pieces on the table: decoherence, entanglement, error correction, holography, inflationary fluctuations. Quantum clocks form a shared toolkit that is tested in labs, in numerical models, and in the sky. Quantum mechanics keeps stirring debates about what is real, what counts as a cause, and what a scientific story should look like. Einstein's old question whether the moon is there when nobody looks captures the worry. If measuring can seem to create the very property we read out, then naive realism struggles. The Copenhagen line treats the theory as a rulebook that links preparation and outcomes. Bohr's complementarity says we cannot assign all classical pictures at once. Which features show up depends on the experiment we run. Einstein wanted more than reliable predictions. He wanted a description of an observer-independent world with definite properties. That split prediction versus description still shapes how people read the same equations and draw different lessons from the same data. Many philosophers and physicists now place the argument inside realism versus instrumentalism. Realists say the success of quantum theory hints that it latches onto deep truths, even if parts will be revised. Instrumentalists say a theory is a tool. It organizes experience and guides action, asking what it is. Beyond that may be a category mistake. Structural realists offer a middle track. They point to relations, symmetries, conservation laws, patterns of correlations that survive theory change, and argue that structure is what our best theories reveal. Some go further with ontic structural realism. Relations are primary, and objects are summaries of recurring patterns. Anti-realists reply with pessimistic meta-induction. Past true theories turned out false, so caution is wise. Realists counter that approximately true is enough to build planes, lasers, and GPS, and that quantum theory's unification of diverse phenomena is hard to read as mere bookkeeping. Mathematics sits in the middle of this. Quantum theory leans on complex numbers, vector spaces, Hilbert spaces, linear operators, and spectra. The imaginary unit appears directly in the Schrödinger equation even though measurements report real numbers. Why does this abstract language match the world so well? One reply is mathematical Platonism. Math exists independently, and physics discovers which pieces reality instantiates. Another reply is nominalism or pragmatism. Math is a human invention that happens to be the right compression scheme for nature's regularities. Either way, quantum work suggests a test. The mathematics that earns its keep is the mathematics that predicts with precision, resists contradictions, and links domains that once looked separate atoms and solids, light and matter, chemistry and stars. Foundations research will stress test these claims with new tools. Quantum processors with thousands or millions of qubits would produce controlled states that are otherwise absent in nature, letting us check whether standard rules hold under deep circuits, long times, and heavy error correction. If small deviations exist, they could accumulate into patterns of faults that betray new physics. Space platforms can test entanglement over planetary distances, put quantum clocks in changing gravitational potentials, and watch for decoherence from cosmic backgrounds not present on Earth. Theory ties these tests to gravity, curved space-time, and information, ideas error, correction, entanglement, wedges, and complexity, so that any anomaly has a home in clear mathematics rather than ad hoc patches. Quantum effects in biology expand the map in a different way. Photosynthetic complexes appear to keep coherence long enough to guide energy along efficient routes. Bird navigation likely uses radical pair chemistry where electron spins respond to weak magnetic fields in a quantum-sensitive way. Hints exist for quantum paths in smell. These cases show that evolution can protect coherence at warm temperatures for brief but useful windows. Claims about quantum roles in the brain remain speculative. Warm, wet tissue is hostile to long-lived coherence at the scales relevant for cognition, and no decisive signature has been seen. Still, the lesson holds. Where a system can harvest a quantum edge, nature sometimes builds the scaffold to shelter it just long enough. Technology built on quantum rules now reaches into metrology, imaging, and navigation. Atomic clocks compare superposition phases so precisely that the best would drift by less than a second over tens of billions of years. Arrays of such clocks test general relativity on tabletop scales, hunt for tiny drifts in fundamental constants, and sharpen navigation. Quantum magnetometers detect fields many orders weaker than Earth's, opening windows into brain signaling and materials. Gravitational wave observatories operate at quantum noise limits. They use squeezed light to reduce uncertainty in one quadrature, while accepting more in the conjugate, trading noise directions the way the theory allows. Similar tricks push electron microscopes, inertial sensors, and radio receivers closer to limits set by uncertainty rather than by engineering. These applications highlight a theme from Foundations. Treat information as a physical quantity. No cloning bounds how data can be copied. No signaling protects causal order, even in the presence of non-local correlations. Error correction shows that delicate states can be stabilized by spreading information so that local noise does not kill the whole message. Entanglement measures tell you which partitions share data, and which act as effective environments. Relative entropy and recoverability bounds quantify what can be reconstructed from fragments, a language that now appears again in holography, where geometry looks like organized information. Some worries that began as philosophy have become engineering constraints. If you want device-independent security, you need a Bell violation big enough to certify entanglement and genuine randomness without trusting black box internals. If you want long-distance quantum links, you need entanglement distribution with repeaters that purify states faster than noise builds up. If you want fault-tolerant computing, you need physical error rates below threshold and enough overhead to keep logical qubits clean. Each task wears the same conceptual badges: superposition, entanglement, decoherence, but turns them into checklists, tolerances, and budgets. At cosmic scales, quantum ideas set initial conditions and arrows. Inflation stretches microscopic fluctuations into the seed pattern for galaxies, turning uncertainty into a sky map that satellites can read. Black holes take those ideas to the edge, where thermodynamics, information, and geometry braid together. Holographic dualities translate hard gravity questions into tractable field theory ones. Quantum error-correcting code pictures explain how bulk regions hide and reveal information. Island formulas and page curve calculations suggest that when the bookkeeping is done in the right variables, unitarity can coexist with horizons, and radiation can carry the imprint of what fell in. The puzzle of time fits the same mold. In labs, clocks in superposition accumulate phase in line with gravitational redshift. Interferometers tie quantum phase to proper time. In theory, time can appear as a relation between subsystems in a closed hole, encoded by entanglement rather than by an external parameter. When geometry is dynamical, the clean split between space and time in textbook quantum mechanics gives way to constraint equations and correlation stories. Those stories gain force when they produce numbers that match tests, from atomic tick rates at different heights to the acoustic peaks of the microwave sky. Realism, instrumentalism, and structuralism, rather than being rival camps to declare winners and losers, can act like lenses you swap depending on the task. When building a sensor, you treat the formalism as a tool. When proving a bound, you reason about structure. When asking why a design works so well, you may shade toward a realist story about what the device couples to. Quantum mechanics leaves room for that plural use while insisting on strict limits. What can be known together? What can be signaled? What noise you must accept? Across scales and disciplines, the pattern repeats. Define the system, track what is measured and what is ignored, identify which correlations carry the signal, and keep careful accounts of where information flows. The details are technical, but the rhythm is steady, unitary. Dynamics where you can, controlled loss where you must, and clear rules for turning amplitudes into outcomes. Against that rhythm, new tools and new questions keep adding layers, and in that quiet layering equations that predict, devices that listen, skies that keep old light, we step back from the puzzle and let the topic gently settle for now.